of outside the or the reviewing kind of stuff before we're back in the book, and on Monday we're back to Saxon. All right. Yeah. So we'll see. But first, some major stuff still coming, as the fundamental theorem of calculus kind of indicates. It's pretty important, right? So here goes. Before I get to the fundamental theorem of calculus, let me get a little background idea. Apparently, on some homework I gave you, I asked two differentials questions, and I didn't actually teach you differentials. My bad. Sorry about that. That said, I do need to use differentials a little, and we will go back over differentials, so don't worry. There won't be a hole in your knowledge. But let me get you one big idea. I think everyone can agree that this is true. dy dx is f prime. Now that's just a mixture of the two notations for the derivative. But the derivative is equal to the derivative. Yay? Okay. Now, dy dx, or Leibniz notation, is a reference of the ratio of change to y, of y to x, or how the two changes relate to each other. As x changes 1 unit, y would change 5 units. Sometimes, however, you don't want to talk about how the changes relate to each other. You just want to say, how much does y change? That's it. Now, if that's the case, then I really need to isolate that how much is y changing, that differential for y. And so I isolate dy by moving that over. In this fact, getting another equivalent must be true fact. dy is f prime dx. Now, in plain old English, what you're looking at there is a small change in y is the result of taking a ratio of change in y to change in x, and then multiplying that by a little change in x. All right? Think proportions. You know, if I told you there's some curve where the slope at the point, dy dx, is 5, or 5 over 1. That would imply that for every x change of 1 unit, y would change 5. Now, that said, I don't necessarily have to change x by 1 unit. Maybe I want to change x by 2 units. In which case, if x changed 2 units, then y would change by 10. It's just simple proportions, all right? Now, what we're going to be doing then is, instead of doing an obvious proportion, we're saying, all right, if I want to always be finding how much y changed here, I could, besides doing this proportion, I could just say dy is 5 over 1 times any old change in x. And then if x was 2, then great, y is 2. Change in y is 2. So we don't have this proportion take place. Now, how is this going to relate to this definite integral? What's that got to do with definite integral and area? Oh, gosh, this is so beautiful. It's like all these a million things coming together. First, though, let's go with a graph. Sketch a curve, but rather than call it f of x, we're going to think of it as the derivative of something. Can I actually pause and math geek out on you for just a second? Okay. It occurred to me yesterday that you don't appreciate analytic geometry. Do you feel like you appreciate analytic geometry? Do you even know what analytic geometry is? No. Silence says no. Okay. So this is so cool. Just so you appreciate what you've been handed. It was for years, and I'm talking millennia, the idea that geometry was, hey, here's the idea of geometry. Okay, here's the shape or squares or rectangles. Okay, and if you wanted the area inside a lake, actually goes back to Archimedes. The guy would say, hey, I had this lake, and can you tell me what the area is inside this lake? He says, well, it's kind of a funny shape. I don't really have a formula for that, but I could do rectangles and say, well, there's pretty good estimate. And then I could do some area, some more rectangles here, and I could squeeze one in there and measure and all that good stuff, and eventually I'd get a pretty good estimate. Now, after doing all those rectangles, he was exhausted. And so he decided to name his method area by exhaustion. That's actually the name of finding an area by all those rectangles, area by exhaustion. Now, for years, that's how area was done, area by exhaustion. I'm talking thousands and thousands of years, almost 3,000 years it was done by that. At the same time, over here was developing the ideas of algebra, which comes from an Arabic word, all that, that's the in Arabic. I don't know what jabra is. I feel kind of stupid, but algebra is an Arabic word. They were the keepers and actually pushed algebra forward huge, big time in the Middle Ages. At any rate, there's all this algebra knowledge going on over here unrelated. I could solve equations, and it was super fun, and I could do quadratic, all this great stuff, right? But then somebody said, you know what, we got to get these two together. They're so cool. We should really fix them up. So they said, what if you created kind of a space where things have kind of standard measurements? And I could put geometric figures on this thing, like a semicircle, and instead of just saying, it's a circle with radius 2, I could actually write an equation in an algebra kind of way for all these points. For example, I could say, well, if I were to say, at any point, x squared plus y squared equals whatever 4. And algebra and geometry got married and had a baby, and that's analytic geometry. Isn't that cool? I give up. You people are really hard to amaze, man. What does it take to amaze you? Jeez Louise. Okay, forget it. Never mind. Yeah. Too little, too late. I don't buy it. Sorry. All right. At any rate, it's awesome. It also allowed for the calculus to kind of come in and use calculus type area. So say now we wanted to do the area of some funky figure, but using calculus instead of exhaustion. Now we were doing area under this curve by exhaustion. We have been doing rectangles. So we were doing exhaustion method there. And you might have come to the conclusion that, man, this is hard, or this stinks, or this is a lot of work. Okay? And to which everybody would say, yeah. And then it's logical to say there's got to be a better way. Well, here's the thought process. Genius, and I'm talking Newton and Leibniz, said, all right, I can use this calculus stuff. Check this out. Rather than name this curve f of x, which I've been doing when I did the limit, when I said, all right, rectangles are delta x, and the heights are f at some x, and I'm summing them all, and I'm taking the number of rectangles to infinity. You follow? We did that, and it was lots of fun, but it was work. And furthermore, it was limited. We have formulas, we have squares and cubes and stuff. We were able to do x squared. But what if I said sine of x? There's no formula for the sum of a lot of sine at different places. There's no formula for that. So we kind of limited in what we can find areas for. So, oh darn it, there's got to be a better way, and here it comes. Instead of calling this f of x, I'm going to say, you know what? It could be the derivative of something. I'm going to call it f prime. And think of it as the derivative. Now, if I do that, then this more would be now the derivative here. The area, the heights would be that f prime value rather than that. Cool? All right. Now, the thing, though, is we didn't just stop at one rectangle. We took the limit. And as we take infinitely many, then delta x's, instead of defined that gap in x, we take it infinitesimally small, and we need a clearer name. So let's call it, I heard it, dx, yeah. Infinitesimally small, what Leibniz called the smallest non-negative quantity, or smallest positive quantity, and he got laughed at for it, is the differential dx. It's also the case that this Greek s, I know it looks like an e, it's an s. Okay, that Greek s, it's cool, but not cool enough. So instead of a Greek s, let's call it a Roman s. Now that Roman s looks like that. And with that, then, it starts to become this kind of thing. And we also need to kind of say, get something in there about how wide the region is. So if we're going to find the area from A to B, let's say we'll put it here. Okay? Now there. Okay, all that's super and all that's great, but still, why the calculus? Why the antiderivative? What's the answer? All I've done is done a bunch of area mumbo jumbo and playing with the sums. Okay. So why the calculus? You might say, well, because that means antiderivative. No, that means sum. It doesn't mean antiderivative. It means sum. Why the antiderivative is this. This area here. Each little tiny area is a base times height, the base of which is this dx, and the height, actually I'm going to reverse the order, the height of each of these is f prime at some point, and the base of each is dx, yeah? The derivative, the rate of change times a small change in x. That looks familiar. Uh-huh. When you take the derivative or rate of change times a small change in x, that gives you a small change in y. A rate of change times a small change in x gives you a small change in y. Small change in y dy. So if I then add all those areas, when I add all those areas, I'm getting the sum of many small changes in y, which I suppose logically would say that means the total change in y. The original function that was before the derivative. Well, the total change in y would be something like y at the end minus y at the start. And y at the end would be y of b minus y of a, and then considering that f prime was the original, or is the derivative, then y should probably be called f of b minus f. Now, just so we're clear, all through all that magic here, to find the area under the curve, instead of all this summation stuff and formula stuff and cleanup stuff, you can just take the antiderivative and evaluate it at the upper minus the lower limit and call it good. Now, I could talk about something because man, this is amazing, but just to amaze you further, because I can tell you, rapture, like in Clinton, I can tell you you kind of dig this, I like that. Do 2 dimensions equal 1? Okay, 2, because we just proved it. If I did the area under f prime, okay, we just did the area under f prime. This 2-dimensional space, if I broke this into square centimeters or something and measured it, then it would be exactly equal to the length or the distance between what f of x, I don't know what f of x looks like, I'd have to take the antiderivative, but if I took the antiderivative of that, graphed it to scale, and then looked at the difference between f, actually let me go this way, f at a and f at b, this distance would be exactly equal numerically to that area. That's amazing to me. The area under f prime is equal to the linear distance between the two curves of the antiderivative. That's crazy. That's insane, man. Are you with me? Oh my gosh! That blows my mind. So, just so many ways. I've been teaching this 8 years. I'm a total nerd. I just sit around thinking about the fundamental theorem. Just thinking. It's one of my favorite things to do. And I still am thinking of things I didn't even, there's still stuff. I honestly hope I get deserted on an island someday so I can just sit around and think about the fundamental theorem of calculus. Wouldn't that be great? Anyway, that said, isn't it amazing? Furthermore, isn't it amazing that I actually found a light that somebody that geeky could get a life. Isn't that crazy? That also is crazy. All right, so the world is amazing, is what I'm here to say. And if you're a total nerd, then there's hope for you, okay? So that was hard. The fundamental theorem actually solves tons of problems, just tons of problems. One, like multiplying by a moving factor. I'll talk about that tomorrow because that's also one of my favorite things to talk about. But for now, we'll talk about, let's do this area now, but in a calculus way instead of a geometry way. That's one of the things I want you to get out of today, and I hope this is a review. I know you did it in the last 6 weeks, but I think you practiced it pretty well, so hopefully it'll go well, all right? If it says no calculator, then make sure you do no calculator. And these, by the way, in invisible ink say no calculator. Right there. All right then. So let's go through this. I'm a little picky about this. If I just taught Calc 1, then I might not be as picky, but because I need to get you leading into Calc 2 ideas, I'm going to be picky about how you set this up, all right? So please pay attention to how, I set this up because I have a reason behind it, even if I might need a little extra symbols here and there, all right? Let me explain. Say you want the area enclosed here. If a sketch is possible, I would strongly recommend you make it. And that is, in this case, that you would have a parabola with roots at x minus 5 and x plus 2. Wait. And it's opening up, and so it would look something like that. The x-axis encloses the region, and so we're looking at that. My picture almost looks circular, but it's most definitely not circular, right? All right, pause for a second, and let's talk about positive versus negative. Positive answers or negative answers. There are some times when you want to differentiate or integrate, integrate and get a negative answer. Give me a possible case where you would want negative. Where it's important to see that negative. I'm not making my question clear. If you're in physics, does negative mean something? Okay, so for example, if you integrated something in an integrated velocity and came up with a numerical answer that was negative, what would that indicate? Yeah, that you moved backward the whole time, or just that you ended in a place backwards of where you started? Yeah, relative to where your axis and all that stuff. Okay. My point though is a negative is good there. It tells you something. You move left or you move down or whatever. Negatives are good. Sometimes, however, negatives are not good. For example, if it says the area. If it says an area enclosed by, that's more of a geometric area. The implication is that you should be expressing a positive answer. All right? Now, this is where the part where I'm picky, okay? It's not okay for me, and it's not okay in my class for you to just slap some calculus at it. And if you get a negative answer, then you do some kind of weaselly workaround. Say you got a negative area here. What's one way you could work around it? You could switch limits of integration, and that actually makes some sense. I don't prefer it. What's another one? I have a lot of people, this is actually taught at other schools, where people just say, you know what, just slap some absolute value on the other stuff, and then boom, problem solved. That's just crap. That's ridiculous. You will never do that in my class. You will never get a negative answer and say, I'm just going to raise the negative and pretend it's positive. I know, I do the problem. I know it came out negative, okay? I know you messed up. So please, you're going to get positive answers by taking, this is positive area, you're going to get that by taking positive components. And by that I mean, if the base is positive and the height is positive, the area will be positive. There's no doubt about it, okay? Here's then how I want this expressed. When you go to do this, to get, now the base, dx, That's always positive because by definition, we go left to right. That's established, and dx should be positive. It will be positive. You need to do nothing there. Always positive. But for the height, if I just use f of x, what kind of f of x values are here? Negative. Okay, so then it's sometimes the case that people say, all right, so I'm going to use negative f of x because it's the opposite of a negative, makes it positive, and I understand, and that's fine. But what I want to see is actually going to do this. I want you to do upper minus lower in all cases, partially because then the volumes that we're going to do later will come out. Now, this is just using a stone-cold math fact. If I take a bigger number minus a smaller number, I will always get a positive answer. Always. No doubt about it. Every time. Okay? That's the thought behind this. A bigger number minus a smaller number is always positive. If the base is positive and the height is positive, my area will come out positive every time, no problem. So when I say upper minus lower, for any one of these rectangles, what's the upper bound? The upper bound is 0. And the lower bound is points on the curve, and that's x squared minus 3x minus 10. I want to see that. You might think, well, that's so stupid. It's the same as just negative. I don't put the 0 there. I have a reason. Please have faith. The region is from where to where? Negative 2 to 5. Now, it's not that bad because I don't require you to show the distributing step. You can distribute and integrate in one. When you distribute a negative and you then integrate negative x squared, what's the antiderivative? Negative 1/3 x cubed. Okay? When you distribute the negative, get a positive 3x and integrate. What's the antiderivative of positive 3x? 3 halves x squared. And when you distribute the negative, get a positive 10 and integrate, you get 10x. Negative 2 to 5. If you're good at these, at the arithmetic of this, then fine. But if you're not so good and you get lost in it, take a few pointers from an old guy who did this without a calculator for years and years, decades actually. And follow these kind of steps to doing this easily and well. When I evaluate it at 5, the upper limit, I get negative 125 thirds plus 75 halves, plus 50. Do you agree? Do you agree? Okay. At negative 2, negative 2 cubed is negative 8 times negative 1/3 is 8 thirds. Negative 2 squared is 4 times 3 is 12 over 2. I could simplify that. My tendency is to not simplify that, and I'll explain why in a second. And then minus 20. Do you agree? All right. Now, the reason I don't simplify is rather than get a common denominator here, get a common denominator there, add them, and maybe get another common denominator later, these two guys, they're already common. I can put them together. What's negative 125 thirds minus 8 thirds? Negative 133 thirds. Likewise, these two guys have a common denominator built in. 75 halves minus 12 halves is 63 halves. And 50 minus negative 20 is 7. Now I'm ready to get a common denominator, but I only have to do it once instead of twice. So the common denominator is 6. The first term you'd have to multiply by 2, and it becomes negative 266. The next one you'd have to multiply by 3, and it becomes 126 or 89? 189. And 70 times 6 is 420. Wait. So, do you want to add first or subtract first, or what do you want to do here first? Let's do 420 plus 189. What do you see? Because 420 plus 180 is 9. That's 609. All right. And 609 take away 266. That's maybe not so much, but let's see. So 609 minus 300 would be 309. Minus 34 more. 309 minus 34 more. So 343. I get 343. How about you? 243? 343 sixths. All right. Try the next one on your own or with your Math Amigos. It is no calculator. It's a little different, and it's not the x-axis of the curve, it's two curves. Did you get intersections of -2 and 4? If so, it sounds like we're in agreement. Continue on.
That's something else.
Oh, good point. I should have named them, you're right. Sorry. I should have named them different. Sorry. Absolutely. How are we doing? I'm getting 36, which feels a little clean. I don't really see anything wrong. Can somebody give me an amen or no, I don't agree? All right, I'll take that as a yes. I'm getting 36. If you're not getting 36, then let's talk about why. Otherwise, other stuff. Feel good? Okay. All right. In terms of just finishing notes on area before I switch gears, I do expect you to be able to use your calculator to do this, and that includes expanding the window or showing an appropriate window, finding intersection points and storing them, finding the area between two curves, and also being able to write your work. You aren't going to show all the integration work on your paper. What I do expect is that you show the definite integral, including the intersection points with 3 or more decimals, okay? Let me say this really clearly. On the AP test, when they say they grade for 3 or more decimals, that's all the way through. That's not just is your final answer accurate to 3. That's the limits of integration are accurate to 3. You show it to 3. Intermediate steps are accurate to 3. Although you're storing along the way, you have to report 3. Okay? Next, if I give you f of x is this and g of x is that, then I'm fine if you write f of x minus g of x for the area. You're not going to integrate it by hand anyway. I do, however, have a problem if they're y and y, if you in here say y minus y. Okay? If that's the case, if for whatever reason I forget to name them function-wise, I would be okay if you called it, if you off to the side said, let this one be f of x, and this one be g of x, and then you could use f and g. On the AP test, they use function notation. They'll call them f and g, and you'll be able to use f and g. Understood? Okay, let's go to inverse trigonometry. These are tricky. These gave me the hardest time. I spelled implicitly wrong. That's implicity. I meant to say implicitly. Sorry. I will fix that for next year. But let's talk about taking the derivative of an inverse trig function. When you take the derivative of sine, what do you get? Closer. Now, doesn't that seem logical that when you take the derivative of a trig function, you get a trig function? And yet, that's why these are funky, because when you take the derivative of this trig function, you get an algebra function. It's really kind of kooky and really integration-wise misleading. They'll get the rookie all the time on the test because they'll say, here, take the derivative, and one of the choices will be arc cosine. Now, that would be a logical guess to go with, right? Especially if you didn't cover this. And yet, the derivative has nothing to do with the trig. It's algebraic. I don't know if Ms. Karen just had you say, here they are, or whatever, but it's important to me that you memorize them and understand where they come from and be able to do both. So I want to clearly communicate what I expect to see if the directions read, show the work. It says take the derivative implicitly, showing all work. Your goal then is to get the ydx, but to see where it comes from. And then let me start here. Say you didn't know. Man, I don't remember arc sine's derivative. Well, one workaround is that I do know how to take what? Somebody said, oh, no, you know it. Do you know how to teach science here? Okay, well, how do I use that? This isn't sine. How do I make it sine? Okay, 1 over? Not quite. Inverse, okay. If I want to get rid of arc sine, which is inverse sine, what's the opposite of inverse sine? Sine. Now, can I take the sine of this side? Sure, as long as I take the sine of that side. What does that yield? X equals sine of y. Or sine of y equals x, whichever side. I don't feel the same. Okay? Now, that's great. Let's take the derivative implicitly. What's the derivative with respect to x of both sides? What's the derivative with respect to x of x? 1. What's the derivative with respect to x of sine y?
Cosine of y dy.
Cosine of y dx. Now that's what I wanted. I want dy dx, so I can isolate that. Dy dx is 1 over cosine y. And people are tempted to say, there we go. And I understand that feels done. It's pretty simple. But here's the problem. The problem is that the original problem was in terms of y, or in terms of x, excuse me. So your answer should be in terms of x also. So that means I need to take cosine y and dump it and replace it with something x-ish. To replace cosine y, you are going to draw. What do you draw? Draw x equals sine y. The starting fact about this problem, okay? X equals sine y. That yields or implies a picture. What does it imply? Like a little person chasing a chicken? Or what kind of picture are we talking about? A right triangle, yeah? It implies a right triangle. It's right triangle shape. What are the parts of the triangle implied in that statement? I don't know 36 and 90. I wish I did. That would be great. Y is the angle, yeah? You take the sine of an angle, and what's x? SOHCAHTOA. Opposite to hypotenuse. So it's implied that opposite the angle y is side x, and a hypotenuse is side 1. Now, can I replace cosine y via that picture? What's cosine y, according to that tree? Adjacent, yeah. Cosine y is SOHCAHTOA. Cosine y is adjacent to hypotenuse. So I need the adjacent side. What's the adjacent side?
Square root of 1 minus x squared.
Square root of 1 minus x squared. Now I can replace cosine y with square root of 1 minus x squared over 1. And so if I do that, then my final derivative in x terms is 1 over square root of 1 minus x. And our derivative really has no signs of triggering. Yes? Just Pythagorean theorem with the sides I did have. I had the x and 1 via the sine, so I just used Pythagorean theorem. Yeah. Okay, good question. I didn't say that. I should have said that. Now, that's the process if it says implicit derivative. Do the work. That's what I want you to try. Try the derivative of arctangent. As any good math teacher does, I give you the hardest example after I do the easiest one. How'd you do?
Did you not have the square root? Yeah, where did this?
Oh, I didn't square it. Good point. Yes, it's squared, so there isn't a root. You're correct. I messed up. Thank you. Absolutely. Does that look better? Okay. Sorry. Yes, absolutely. Okay. Now, as I said, there's some danger in seeing a trait expression and then getting a derivative that's algebraic. It's really actually the opposite that's the real danger. It's when you look at an algebraic thing and say, what's the antiderivative that can be? I wouldn't, without instruction, not in a million years would I think to use inverse trait on that. I just wouldn't. That's through instruction that you start to see it that way, all right? Before we do that, though, it helps in order to just recognize it. You need to have in your brain that the arctangent of x is 1 over 1 plus x squared, generally speaking, and then we can have some, chain rule part to this, later on. And the arcsine is 1 over the square root of 1 minus x squared. And they look very similar, but tangent has no root, and it's a sum. Arcsine has a root, and it's a difference. You keep them straight in your head. And really, those two are the ones you really need to have down cold. The reason you need to have them down cold is because you'll need to see them coming at you and recognize them in an integral problem. So look at this first one. Let's do this one together. It's the harder of the two. I look at that and I think, gosh, that's definitely not a U sub problem because one's not the derivative of the other on the surface, because x to the 6th derivative would be x to the 5th, and the powers are there, right? And yet you will use U sub here. If I see a sum like this, I'm thinking maybe arctangent, because U sub's not working. So let me start by saying, all right, 1 plus what squared? X cubed, okay. Now that's true. How about that then? If I took the derivative on that, could that be an x squared recurrent term? Yes, the answer is yes, Mr. You bet. Okay, so here's what I'm going to do. I'm going to shoot for arctangent, and I'm going to use a U sub. I'm going to let U equal x cubed, and therefore du is 3x squared dx. Now, it's starting to look good, but I think you can see we have a little constant problem here. So what can I do to work out my constant problems? Multiply by 2/3?
No, divide by
So so these guys will do this the way I thought it, which is a little different. And this can, you guys do it. I want you to do it your way. So how would you, this can, you guys do it. How would you? First of all, does that 2 help you or hurt you? 2? Good? Bad? Bad. All right, what can you do? Put it out front. X squared over 1 plus x cubed all squared dx. Okay? Great. Now, do you have x squared dx, or do you have a little more? Well, you could say du over 3 is x squared dx. Then you could most definitely substitute. Does this look familiar? Is this how this can touch you?
Yeah.
Okay. Okay. Go, if you see that 2/3 thing, by all means go for it. Okay. So if you do that, then the x squared dx becomes 1/3 du over 1 plus, and the bottom becomes u squared. So that when you integrate, that 2/3 is all great. What's the antiderivative of 1 over 1 plus u squared? Arctangent of u plus c, and with substitution back, that becomes 2/3 arctangent of, what was u? X cubed plus c. And then all over the world, there's people looking at the back of their book, doing this problem and saying, wait a second, they didn't know what to do, so they're trying to get started by looking at the answer in the back of the book, and they say, wait a second, yeah, what? Arctangent? That doesn't even have any tangent. I must be looking at the wrong book. No, you're looking at the right thing. It's actually an arctangent antiderivative. You follow? All right. Try that one on your own, which is substantially easier. How's this one going? A little better? Answer? Arcsine of e to the x plus c. By the way, I'm using arcsine, but you can most definitely use this notation. They're equivalent, and they're both accepted in all. Okay. You trying to get out of here without that homework? Just you trying. All right. Oh man. Everybody reminding me, that's for sure. All right. First and foremost, this also is mislabeled. This should be review 12, so it's not to be confused. Please right away change it to review 12, not review 11. I apologize. I don't know. All right. Again, call that review 12, not review 11. We've already done review 11. All right. So I had, this might be enough to just get you a little bit of a start. On review 10, I think it was review 10, there was a sigma notation problem at the end. Yeah?
Yeah.
Okay. Maybe I can get you started real quick. If you recall, the function was this, and if I did right-hand rectangles, I'm trying to put this into my calculator and not have to retype it over and over again. Okay? If you've done this problem or at least attempted it, you're kind of with me, yeah? All right. If you go to the graphing menu, and instead of putting in a function, put in a summation. It's right in here next to 9. There's a catalog button, and the summation notation is right there. Now, this is a function of x. We want to change the number of rectangles, so 4, 8, so on. So, am I looking at using x for n or for I? N, all right. So, you're going to use, instead of an n up there, you're going to use an x. Here will be I equal 1, or you could use k, I suppose. And in here, make sure that everything is in those parentheses. If you just put the 3 over x there, and then everything else outside, that's not what you want. You want to sum the whole thing. So make sure you use ample parentheses, 3 divided by x for the base. And then, how do I get over there? Oh, shoot. How do I scroll over to that place with this? This is not going. You know what I'm talking about? Oh, wait. I did it. Wait. Okay. That might get you started, but if not. Obviously, I didn't get the questions, so nothing to turn in, and tomorrow we'll get caught up, or not. Probably. But have a nice day.
So you don't do it?
So, you want me to keep going? So
The
this,
next part you put 3i.
so this is adds,
Yeah.
adds,
So you leave the
adds,
I.
but the I isn't on.
One day,
I like you, Quentin.
I have to work to make sure people don't like me is why people don't like me.
Who was the problem?
Yeah, it's really good.
I mean, obviously, that's something. They were like, they sent out a post that email that was like, you guys are all doing this wrong, you have to follow the template. And I read that, and it's like, why not? Last week it was like, it was like,
No, I
like, how are you pretty? Are you gonna do calls weekly? Oh, what week are you on?
Dude, look at him. Okay.
Yeah, it was a, not this week, I didn't.
Yeah, thank you.
You want to, like, this summer?
Yeah.
On the next one, number 10, it has the same curve.
Are you on call?
Why? Because is that what you see those?
It's really
Okay, I'll make it.
Ahead of everybody else.
Yeah. Because everyone else will be zero.
I'm sorry, I tried to put it in and then it said English.
Let me see, I had one or two mistakes myself the first time that I reached.
And I've added like a few extra, yeah, stuff like that, trying to get it to work, but it's not. And then I have some questions. I kept 9 because I just realized.
So actually, let me see this. If you want to identify, it's easiest to define a function in the graph. And then if you define it here, you have to do something like F1, and that, but you have to do something like let this equals something. Oh no, it's this one. It's this one. No, that's not it. It's this one.
Done?
So let me see if it's okay, so yeah, although it makes total sense, I hear what you're saying, equals. To identify a function of this, you have to do that little
Okay.
colon thing, and then I think it should- no. That's definitely not what we
I'll
want to
just
do.
figure it out.
Try doing it in the graphing menu, you'll have a better time. Okay, call it F1.
Okay, can you, so just this question, C, understand?
So the idea is going back, you had the square root function, you did a tangent line at 25,
Yeah.
and you want to talk about where that tangent line estimates square root 12. If I call the tangent line y1 and the square root function y2, then I could let y3 be the error in the tangent line estimate. Now, at 25, there is no error because they're perfectly in line with each other. And close to 25, there's no error, there's little error because they're so close to each other. But the further you get away from 25, the bigger the difference between the two. That difference is the error. You know what I'm saying?
Mm-hmm.
And so the further you get away from 25, you get more error. The question says that you're going to call it a good estimate if the difference between the two or the error is less than a tick. Well, if this is the error curve, and I want to know when it's less than a tick, you could graphically graph 1 tick.
The line, okay.
And then wherever this is below 1 tick, you got a little error.
So you want to do it,
So,
intersection.
yeah, exactly. That'll give you the region where you get. Okay. So graph the error. I actually have 4 here. I have y1 for the line, y2 for the square root, y3 for the error. What difference y1 minus y2? And then I graph 110, change this to all the super small.
You did graph y for this.
I did graph y3, which is the error, the difference between the two.
So.
And then I graph.
I
No,
was
that's
a
okay.
little bit lost. So like, I understood like what you were saying, but then, so, y1 is,
It's
there's,
a line equation. That's tangent.
okay, and then y2 is 25.
It's the square root function in the point. And you want to generate that small curve.
Yeah.
And they'll be touching right there.
Subtracted
And then
this and this.
yeah, y3 is the line take away the curve to give you the difference between the two, or where how much I'm off by. So that would y3 then, this curve y3 represents the difference between the two. And so I would expect y3 to be at 25 be 0 because there is no difference at 25. And the error, the difference between them would get bigger and bigger as you got away from 25. So that's what this curve is looking at, that's the error. If you don't want to see what it is, that's the curve. Okay, you back. Do you have a question?
No, but I'm gonna be gone tomorrow, so maybe like this stuff. Shoot.
How about if you just, we're going to do it tonight, or you just going to pull it out for Sunday night?
No, no, because to take the notes, I have to have a sheet.
Like if I watch a video and then.
Yeah, I don't have any, I'm still not but I don't have
Okay.
I will have them done tomorrow at school. I think that's probably it.
Okay, I'll just have someone give me.
Yeah, so you can so when you click on,
Oh, you download them?
yeah, when you click on the day in the calendar, actually I'll show you
Oh,
this.
yeah.
I went in Yeah, you'll see, it'll actually only show up as one attachment because I put the notes and the problem set in together. I just do them in the same.
Okay, yeah, I just forgot that you actually posted it.
I don't even know if I told people this, I don't know. But if you click on the day, there'll be the lesson and
No, I don't have it.
the notes, and just click on and the notes and the problems that'll all be in one.
Okay.
Okay?
You keep carrying us. You keep carrying us.
Yeah, we're getting rid of this. Hi, folks.
What was it for? The thing.
Okay. Hi.
Oh, I got mine back too.
Yes, it is.
Yeah.
That's from when I was here.
Oh, see, I wanted to do college my mom's. I did. I only do it 1 year. It's sunflower. Freaking love sunflower. No. You have to switch
Stop the recording.
Yeah, man.
Start recording.